Alright, students, today I am going to give a lesson on Abraham de Moivre and his famous theorem about complex numbers. So I have a picture of the man here, and he was a French mathematician, deeply inspired by Isaac Newton, as so many people in his time were, and people today still are. He did a lot of work on complex numbers and came up with a theorem that we named after him, de Moivre's theorem, which is really talking about how you do powers and roots of complex numbers. All right, so I'm going to show you where it comes from. First of all, I'm not going to do a proof of it, but I'm going to demonstrate the logic behind the proof on this. So the idea is, if you have a complex number in the trigonometric form that we've learned, like this, then what you can do is you can raise this to a power, and if you raise this to some power n, then it turns out what you do is you raise the radius to that power and you multiply those angles by that. So it's a very elegant, very, very simple theorem that simplifies calculations tremendously. So, for instance, I like to use the example if you were doing 1 plus I to the 100th. Okay, now that's the a plus bi form like that. Well, if you didn't know anything about this theorem, you would really pretty well be forced to write the thing out 100 times, multiply it out 100 times, and you'll get this real simple answer. This theorem allows us to do this very, very quickly and efficiently. So what I'm going to do, first of all, before I do problem number 2, I'm going to give you an idea of how this works. So one of the things that I'd like you to write down is, let's just take an arbitrary complex number. Again, we call this the r cis theta form, where we have r cosine theta plus I sine theta. And what we're going to do is we're going to take this thing, let's just work with the third power, right? And this will demonstrate to you kind of the logic behind de Moivre's theorem. It's actually very simple. So if we wrote this out 3 times, and I'm going to write this out like this, we would have r cosine theta plus I sine theta, and then we're going to just write it out 2 more times like this. And you'll have to apply a rule that we learned in the previous section to really understand this now. Oh, I'm doing the wrong thing there. Okay, so the idea behind this is we learned this basically, and I'm just going to review this at the top here. So for instance, if you had something like 5 cosine, say, of 60 degrees plus I sine of 60 degrees multiplied by, say, 2 times cosine of 30 degrees plus I sine of 30 degrees, all right? Well, what we learned how to do in this is, in the previous section, is how easy it is to multiply out 2 complex numbers in the trig form. What we do is we do 5 times 2. And then what we do is add the angles. So we would have 60 plus 30. So we'd do the cosine of 90 plus I times the sine of 90. So we'd end up getting a result of 10 cosine 90 plus I sine 90. Okay, that's what we learned last time. So the logic behind this is going to be this, right? Well, what we'd do is if we extended this to 3 numbers and 4 and so forth, we would just take r times r times r. So we would do this. Okay, then we would add the angles. So we would just do cosine and then add the 3 angles. So we would do theta plus theta plus theta, then plus I times sine of theta plus theta plus theta, like that. Okay, now the idea is, notice on this would be r to the 3rd. This would be cosine of 3 theta plus I sine of 3 theta, like that. Now that's what de Moivre's theorem basically tells us to do. So if you have a complex number to the 3rd power, you're going to take the radius to the third. Then you're going to multiply those angles by 3. So if you did this same logical process through 4 complex numbers, you just have r to the 4th, cosine 4 theta plus sine 4 theta, and so forth. Now that's not really a proof, but it's a demonstration that helps you understand the why part behind de Moivre's theorem. Okay, now what I'm going to do is I'm going to erase some of this that I've done up here, and I'm going to run through some examples of using de Moivre's theorem. Okay, so that's the idea behind that. All right, now what I'm going to do with this is, on this particular problem, of course what we have is we have a complex number, and it's raised to the 5th power. Okay, so in de Moivre's theorem, we consider n to be that power, and of course the radius is going to be 2. So what we do is we do 2 things. To work this problem out, we're just going to take, according to de Moivre's theorem, we're going to take 2 to the 5th, then we're going to multiply that by the cosine of 5 times 60 degrees plus I times the sine of 5 times 60 degrees. So de Moivre's theorem is very easy to use. So you'd end up having 2 to the 5th is 32. Then you would have the cosine of 300 degrees plus I times the sine of 300 degrees, like that. All right. So what we'd end up having then is we could go ahead and go to the unit circle and work this out. Now, if I wanted to leave this in the trig form, this is the answer in trig form. So in the trigonometric form, we would just leave it like that. All right, now if we want to go to the unit circle, well, we could do this then, basically. So let's just kind of consider what's going on at 300 degrees. Okay, so at 300 degrees, remember you got these 3 critical points in quadrant 4. 300 degrees is this angle right there. And on the unit circle, that is the square. Whoops, doing that wrong already. The way I always remember this is the x value is small and the y value is is bigger at this angle like that. So anyway, we got those numbers. So what we're going to do is the cosine of 300 degrees is 1/2. The sine of 300 degrees is negative square root of 3 over 2. So all we got to do is just substitute this in. So we'll have 32 times 1/2 plus I times negative square root of 3 over 2. Then we can multiply this out. So if we do a distributive property, we're going to have 32 over 2 minus, and I'm going to write this as 32I root 3 over 2. And then I'll just reduce the fraction. So I have 16 minus 16I times the square root of 3. Okay, and that would be the answer to the problem. So it's very simple to do de Moivre's theorem. It's a very elegant result, as we find with this new system of writing numbers. Okay, all right, so that's a pretty simple beginning example. So let me pause. Okay, so we're going to do another example. And this time the n is the 3. So that's just the power in the formula. And then the radius is going to be 2. All right. So de Moivre's theorem tells us to do this. You take the radius to the 3rd power. Then you're going to go cosine of 3 times 45 plus I times the sine of 3 times 45 degrees, like that. Okay, it's going to work this out. So we have 2 to the 3rd is 8. Then we have the cosine of 135 degrees plus I times the sine of 135 degrees. Okay, so if I wanted the answer in trig form, you're already done. All right, so it's real simple just to leave it in trig form. Just to kind of, for review, I want to go ahead and just take this out all the way to the a plus bi form. Okay, so what we want to do on that again is just draw ourselves a picture of a unit circle and reason out the details on this. So on a unit circle, you're looking at 135 degrees. 135 degrees would be halfway in between, like this. So that would be at the point negative square root of 2 over 2 and square root of 2 over 2. Okay? So we're just going to fill in the details. That's the cosine, of course, and this is the sine. All right, so what we would do is, to get our answer, is we would say 8 times negative square root of 2 over 2. Come on. Sometimes I can't write and talk at the same time. Okay, negative square root of 2 over 2. It's what's part of it, the aging process, I think. Sine 135 is going to be square root of 2 over 2, like that. Okay? All right, just multiply it out. So you'd have negative 8 root 2 over 2 plus 8I root 2 over 2. So I'm going to reduce that to negative 4 root 2 plus 4I root 2. So that would be the A plus BI form answer to the problem. Okay. All right, so that's the Moivres theorem. It's very simple to do. Simplifies calculations quite a bit on complex numbers. Okay. All right, so I'll move to the next page, and this is the kind of the one that will wow you. It's guaranteed to wow you, and just going to impress the heck out of you. All right, so the idea with this one is we're going to take 1 plus I to the 20th. Well, if you were in college algebra, and if you didn't do Moivres theorem, of course, you just have to write it out 20 times, and you just have to deal with it. And you'd be working on it for a long time, and you probably would make a mistake because of the calculations in it. Well, what we do in Moivres theorem on this, then, is the first thing we're going to do is we're going to start by converting the 1 plus I. We're going to take the complex number 1 plus I, and we're going to convert that to the r cis theta form, the trigonometric form. So we have to start that way. All right, so if you're plotting the complex number 1 plus I, you're simply going to go over 1 on the real axis, and then you're going to go up 1 on the imaginary axis. So you're going to have a point up here like that. So let's go ahead and draw a nice diagram to show what's going on in the problem now. Okay, so we have that complex number. And really what we have on this is we got to figure out the radius and the angle on this. So it's actually very simple. So first thing is, I'm just going to bring that down at a right angle. Of course, this base of this triangle is going to be 1. Since we went over 1, the height is also going to be 1. Now remember, we have a special triangle that goes 1, 1, square root of 2. And those have the angles 45, 45. So that's a 45, 45 right triangle. So what you would end up having then, see, is the radius is going to be square root of 2. C stands for the cosine, so that's going to be cosine of 45 degrees. I is the imaginary unit, and then the S is the sine of 45 degrees, like that. So what we've done is we have changed this into this form. So the 1 plus I just changes into that form. Okay, so what we're going to do is we're going to take this to the 20th power using the Moivres theorem. So we're going to use square root of 2 times cosine of 45 degrees plus I times sine of 45 degrees. And we're going to work that out. So the Moivres theorem is very simple. It just says take the radius to that power. So we're going to take the square root of 2, and we're going to raise that to the 20th power. Then we're going to do the cosine, and we're going to multiply. We got 20 groups of 45 is the way I think of that, plus I times the sine, again, of 20 groups of 45 degrees, like that. So we're going to work out the details. We're going to use a unit circle to help us through this. There's a couple of issues that frequently show up with students. I see a lot of students don't know how to deal with this part effectively. So a lot of times they rely on your calculator. Don't get your calculator out for that. That's silly. And here's why. If you had something like the square root of x to the 20th, that's x to the 10th. Okay? Now why? Because what is a square root? Whatever your answer is, if you multiply it by itself, you're going to get what you started with. Okay, so if you had the square root of x to the 100th, that's x to the 50th. And after all, remember that a square root's just a 1/2 power. Okay? So what we're going to do with this is we're just going to write this as the square root of 2 to the 20th. And so you can put that 20 under the radical. Because technically that's, if you have something like if you had the square root of 2 to the 3rd power, all that means is this. So that is the same as the square root of 2 to the third. It gives the same result. Okay? And then what I'm going to do on this is I'm not going to multiply that out. You could multiply it out if you wanted to and get 900. But what I'm going to do is I'm going to show you just how to count that out on a unit circle. Okay? So I'm going to do that to get the final answer. So basically, what we would do then to finish this up is just these things. All right, so I'm going to draw a little picture of a unit circle diagram again, like this. Okay, now I'm going to count out 45-degree chunks. Okay, so I'm going to put like a dot there. I'm going to put a dot at 45-degree increments, and we're going to count. Okay, like this. So watch how I do this then. So I'm going to go starting here, 0. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 groups of 45. Then we can keep going. 9, 10, 11, 12, 13, 14, 15, 16 groups of 45. Then we go 17, 18, 19, 20. So we're here. That's all that matters is we're here. So on the unit circle, we get -1, 0. Okay, like that. So that's going to mean that the cosine is going to be -1, and the sine of 900, or this point on the unit circle, is going to be 0. So now we're ready to write our answer. So we would get the square root of 2 to the 20th is 2 to the 10th. Cosine of 900 is -1. And then this would be I times 0, so you'd have this, right? So 2 to the 10th is 1,024. And then if you multiply that by -1 plus 0i, you get the final answer, -1,024 plus 0i. Okay, that's in the complex form right there, so that would be your solution to the problem. So it's very easy. Okay, it didn't take 1, 2, 3, just a few steps to work this out. Otherwise, you would have had to have multiplied that thing out 20 times, so that's kind of the idea. Okay, all right. So that's kind of a nice example. I think that should wow a student. Okay, we found a super easy way to doing this by looking at this new form of complex numbers. That's a theme that's repeated over and over again in mathematics. We look at some new idea and it leads to something different, oftentimes simplifying the process that we have been doing in the past. All right, the other thing that I do like to show students on this is a TI calculator also can do basic computations. Please don't do your homework this way because you won't learn squat if you do it this way. But what you can do is use this for checking. I totally would say that's an okay thing to do, right? Mathematicians, if you're in more advanced classes and so forth, you might want to use more technology on these kind of things. But we're learning the concept here. So you'll notice that you have the letter I right there. And what you can do is you can just put parentheses. You can put 1 plus I. To get I to come out, you go second decimal, close parentheses. Now let's raise that to the 20th power. Look at that. 1,024 came out. Now that, I would think, would wow you. It's got to wow you. Okay. That's pretty amazing. All right. So let's move on to this next one here and look at one more example of de Moivre's theorem, and then I'll let you work on a problem. Okay, so this one. Okay, so I'm going to start this problem the way I've started the other ones. We're going to convert this complex number, which is in the a plus bi form. We're going to convert that to the trigonometric form. Okay, so we're going to work at 2 minus 2i, we're going to have to convert that to the r cis theta form. All right, so again, when we're plotting this complex number, you're going to go over 2 on the real axis, and then you're going to go down 2 on the imaginary axis. So you're going to put a dot there, okay? Now we'll, of course, just draw the radius. So we're looking at this diagram like this, and we're ultimately going to kind of see if we can get a triangle out of this and have enough information to figure that out. So basically in this problem, this part of the triangle is represented by 2. This part of the triangle is represented by -2. So that's really the b value. That part of the triangle is a positive number, but we're going to represent that by 2. Okay, so the first thing we'd have to do is we'd have to crunch out, of course, the radius. So we know that r squared equals a squared plus b squared. Remember, that's the a part of the complex number. That's the b part. So we're going to have r squared equals 2 squared plus negative 2 squared. So that's r squared equals 4 plus 4. Whoops. Might want to put your equal sign there, Brad. Come on. So now we're going to have r squared equals 8. Square root both sides, so we're going to have r equals square root of 8. And of course we can break that down into 4 times 2 to get 2 radical 2. So I'm going to represent that radius by 2 radical 2. Okay. Now the other thing is consider this angle. Now what I do, this is a right triangle, and anytime these sides are the same, it's going to be a 45-degree angle. One thing that you can do, if you want to, is you could divide everything by 2. You don't change the angle, you would change the radius, but we already got the radius, that's set. And if we did that, see, this would become -1. This would become 2 divided by 2 would be +1. And then this thing would be square root of 2. So see, we're back to the 1, 1 square root of 2 triangle. So that's 45 degrees. All right, so we have that as a reference angle. All right, now you don't want to use 45 degrees. You could use either 315. So you could say theta is 315. Or, and this is my preference in this problem, I would use -45 degrees because it's easier to work with. Ultimately, it's your call, though. So what I'm going to do is I'm going to write this as I convert this, the radius is 2 root 2. Then we're going to have cosine, and I'm going to put in -45 degrees plus I times sine of -45 degrees, just because it's a smaller angle. I'd rather deal with that angle than I would 315. I can probably do everything in my head if I do that, see. Okay, so this is your trig form of your complex number. So see, you have to start by converting 2 minus 2i to that form, like that, okay? Now we're ready to apply the Moivres theorem, okay? So to begin with on this, we're going to take this complex number, 2 root 2, times, and I'm just going to write this, I guess, kind of like this, cosine of -45 degrees plus I times the sine of -45 degrees. And I'm going to raise the whole thing to the 5th power, okay? All right, so de Moivre's theorem, you're going to do these things. You're going to take the radius, which is this thing, and you're going to raise that to the 5th power. That's the problem area for students right there. I'll kind of review how you do that now. Okay, then we're going to do the cosine, and we're going to do 5 groups of -45 plus I times the sine of 5 groups of -45 degrees, like that. Okay, you kind of get a lot of parentheses going on in this problem, don't you? Okay, so I got everything there, like that. Okay, so that's how de Moivre's theorem would do, is take that to the 5th and multiply the angles. Okay, well, this part right here, let me just focus on this part, because this is where students sure do have make a lot of mistakes. The idea with this is that basically this could be written as, and I'll just kind of write this down here, if you have 2 root 2 to the 5th power, you're multiplying this out 5 times. If you multiplied it out 5 times, and I'm going to do this just to help you understand this, because this is an algebra issue that needs to be covered with students who have some algebra weaknesses. So you'd have 2 times 2 times 2 times 2 times 2. Well, that's 2 to the 5th. Then you have 5 groups of those square roots of 2, so you could write that like that. Okay, well, 2 to the 5th is 32. All right, and this, you can break this up like this. You say 2 to the 4th times 2 to the 1st. Now, the reason I do that is because 2 to the 4th is 2 to the 2nd when you take the square root. You get half of that exponent, so you'd have 32 times 2 to the 2nd times the square root of 2. So if you put that together, you'd have 4 times 32. So 4 times 32 is 128 radical 2. Now that's one way to look at the problem. Now what I'm going to do on this is I'm writing my steps on this in this problem. I'm going to write this like this. I'm just going to say, okay, that's 2 to the 5th. And then this is the square root of 2 to the 5th, like that. Okay, then I'll bring this down. And then by the same logic, now you don't have to multiply this out, but you could if you did multiply that out. Let's see, that would be negative 225 if you did that. And same thing here. Okay, so again, this thing right here, you just really do like this. You do 32, you break this up into 2 to the 4th times 2 to the 1st, and we can bring this down. Or you can just kind of crunch out that radical at the side of your paper so you don't have to write all these steps like this. So anyway, that gives, like we did down here, see, that's going to give 32 times 2 squared times square root of 2, and then that's going to be 128 times the square root of 2. Okay? Now, what I'm going to do from here is we're just going to consider what's going on the unit circle. Okay, like this. All right, so you want to study how I did that arithmetic on that radical. That's like real super important on this, that you get that down. Okay, and don't struggle with that. So I'm going to erase this scratch work I did down there. You can always backtrack and review anything you need to do on the video, of course. So what I'm going to do is we're going to just count out groups again like this. I like to kind of remind students that you can look at it this way. This is just kind of my preferred way to look at this. I just count out 45, so I've got, just kind of put a dot at 45 degrees and count them out. So see, we got 5 groups of this. There's 5 groups, so I just go 1, 2, 3, 4, 5. So that would be at the point negative root 2 over 2, root 2 over 2 on the unit circle. So now you're ready to crunch this out. So the cosine is going to be this. The sine is going to be this. Okay, now you're ready to crunch out the answer. So you would end up having 128 root 2 times negative square root of 2 over 2 plus I times the square root of 2 over 2. Like that. Okay? All right? I just like to kind of show students how to count things out because it simplifies things a lot of times when you do that. Okay, now we just do a distributive property and multiply it out. So we're going to have, notice on this, you're going to have negative 128. You'll have the square root of 2 squared over 2. And then you'll have 128, again, square root of 2 times square root of 2 is square root of 2 squared times I over 2. All right, so when we square the radical, that's going to come off. So you're going to have negative 128. And you can go ahead and write that at 4 if you want to. Okay, all over 2. Same thing here, 128. That's going to be just 2 to the 2nd. So that's going to be 4. Remember, that's, hold on. That's not right. What in the world am I doing? I know better than that. Square root of 2 squared is half the exponent, so that's 2. Okay, and then the same thing here. Okay, again, if you're doing the square root of 2 squared, you get 2. That's the square root of 4. Right? So then we have this times I over 2 like that, and then we can cancel out the 2. So the answer to the problem is negative 128 plus 128i. All right, that's it. Now that is cool. I wrote a lot of excessive steps on that. The main issue with this problem with students is this radical. That's what you got to study. That's the algebra background issue more often than not that causes students problems on this kind of stuff. I encounter that over and over again. Okay, now I'm going to do a quick check on this problem. We can do this on the calculator. I encourage you to do this. So we're going to go back to the original and put in 2 minus 2i. Like that. What in the world am I doing? Okay, 2 minus 2i. So you go second to get the I to come out, and then raise to the 5th power. And look at that. We get the answer. Now that is just amazing, isn't it? So again, I know you're being wowed. I just think this stuff's amazing. All right. Okay, so let's move on. Now I'm going to let you all work out these next 2 problems. So I'm going to pause my recording. You should do the same and try to work these out. Okay, so let's see how we did here. All right, so this one is already in the trig form. All right, so what we're going to do is you're going to take 2 to the 5th by de Moivres theorem, and then you're going to do 5 groups of 120 degrees, and then I sine of 5 times 120. So you should have started off the problem like that then. Okay, 2 to the 5th is 32. 5 times 120, it'd be a little lazy here. 5 times 120 is going to give 600. That's what I thought. Okay, so cosine of 600 degrees. I should have. 5 times 12 is 60, Brad. Okay. All right. You know, and I try to set a good example for students too. Okay. Don't try to do stuff in your head. Sometimes I get lazy though too. All right. So let's see. We get 600 degrees like that. And then we're ready to basically just go to the unit circle. So I'm going to draw a unit circle diagram here, kind of figure out where I am in the grand scheme of things. Well, one thing we know is that we have 600. If you subtract off 360, you'll end up having 240. So really the way I look at this is I'm just going to count this out kind of like this. So I'm going to go 1 lap around the circle is 360 plus 240 more. So 240 is going to occur down here somewhere. Okay, so I'll just put a diagram there for 240 degrees. So all we got to do is figure out where that is on the unit circle. So 240 degrees is what matters. Okay, all right, and if you kind of count this out, like you would have 180, this would be 210, this would be 225, so we're at 240. Okay, so that point on the unit circle is all that we need to figure out. And that point on the unit circle goes like this. That's going to be the one that has a small x value, that is negative, and a big y value, which is negative square root of 3 over 2. Okay, like that. All right, so now we just crunch it out. So the cosine of 600 is this. The sine of 600 is this. And we simplify the algebra. So we have 32 times negative 1/2 plus I times negative square root of 3 over 2. All right, when we do this, multiply straight across, you're going to get negative 32 over 2 minus 32I root 3 over 2, like that. So this is negative 16 minus 16I times the square root of 3, like that. Okay? So that's how that would go. Now, one thing I'm kind of curious about, I haven't tried this in a long time, but I thought I'd just try it and see what happens. If you had your calculator in degree mode, and if you wanted to check this, you would have to put it in like the original problem. You'd go 2 parentheses, cosine of 120 degrees, plus, now you can put the I in because you do have the imaginary number there like that, times sine of 120, like that, and then you could raise the whole thing to the 5th power. I'm just curious of what comes up, okay? That's kind of interesting, okay? I think I got everything put in there okay. I got the 5th power put in there and everything. I got the radian mode and everything like that. I figured that probably should work. I've never tried that before, so I was just kind of curious, but when I see that -1, that makes me awfully suspicious on that, so anyway, you can try that if you want to. Yeah, I think I must have put something in there wrong. I'm gonna try that one more time. I must have missed a parenthesis. It should work. So let's see, 2 cosine 120, like that. See, that's okay. Then plus I times the sine of 120. I'll close parenthesis. Then I'm gonna double the parenthesis like that. Let's see. I think I might need one more parenthesis. Go to the 5th power. Ah, there we go. Okay, I missed a parenthesis on that. That's what my problem was. Okay, I figured it would work. Okay, so notice on this, well, there's the negative 16. That's good. Now, if you looked at this this piece right here, if you looked at the 16 root 3, so if I go 16 times the square root of 3, on that, see, that matches the 27 like that. Okay, so yeah, it does work. Okay, I thought it would. I just never had the thought of even trying that. Okay, so let's see what we did on the next problem here. So the next problem, the first thing that you want to do with this is you want to do a unit circle diagram to convert this complex number over. So you have negative square root of 3 plus I. Okay, so what you should have done is you just are going left and up. So we're going left over some amount and then up 1 like that. Okay, so we are in quadrant 2. So we want to get a reasonably good diagram to help us kind of reason out the angle and the radius and everything. Okay. All right, so draw a triangle, right triangle down to the x-axis. This side, the b value, would be represented by negative square root of 3. This side, the a value, would be represented by 1. Okay. And see, we know that we have the 1 square root of 3, not square root of 2, 2 triangle. This is the problem that I say is as easy as 1, 2 square root of 3. Okay. Well, it goes like this. This is a 30, 60 right triangle like that. So what you would end up having then is you would end up having, well, the radius is equal to 2, and then theta. Now, you don't want to use 30. You want to use, of course, 150 degrees. Okay? So theta is 150 degrees. So what we're going to end up having is when we convert this over, we're going to have negative 3 plus I just converts to, in the r cis theta form, 2 times cosine of 150 degrees plus I times the sine of 150 degrees, like that. Okay? So what we're going to do is take that to the 6th power. So let's write out 2 cosine of 150 degrees. You got to have a parenthesis right there now. 150 degrees plus I times sine of 150 degrees, like that. Okay? Now, see, I need another parenthesis there, all right? All right, and we're going to take that whole thing to the 6th power like this. All right, so when we do this, the Moivres theorem says take 2 to the 6th, which we'll do, and then let's do 6 groups of 150 degrees. Okay, so we can do this. So 2 to the 6th, I think, is 64. And then if you do 150 times 6, I think that's 900. Because 15 times 6 is 90. Okay. 6 times 15. What the heck am I doing here? God. Okay, 6 times 150 is going to give 900 like I thought. Okay, so we got cosine of 900 degrees plus I times the sine of 900 degrees, like that. All right, then we're ready to move this to the a plus bi form. Now remember, if we were just wanting to have the answer in the trig form, this would be the answer in the trig form. So the a plus bi form, we just need to work out a couple of things on this then, okay? So, going to go back to the unit circle to finish this up. So just kind of consider where 900 degrees is. So you got 900. You can subtract 720 from that. And if you do 900 minus 720, you're going to get the angle that really matters is 180 degrees. I should have been able to do that in my head too. Okay, so what you're really doing is 2 laps around the circle, which is the 720, and then the 180 more. So for all practical purposes, what matters is that's the point on the unit circle. So when we do the cosine of 900, that's negative 1. When we do the sine of 900, that's equal to 0. So what we'd have is 64 times negative 1 plus I times 0. So that is 64 times negative 1 plus 0i. So the answer is negative 64 plus 0i. That's pretty simple, okay? All right, and with this problem, you could actually do this in the calculator like this. You could go negative square root of 3. You got to close parentheses, plus I. And then raise that to the 6th power. And look at that. We got negative 64. That's amazing. Okay, so very good. Hope you did well with those problems. So I'm going to move to the next thing here. Okay, so we can kind of do de Moivre's theorem in reverse by finding roots of a complex number. So what we'd be doing is looking at like square roots and cube roots and just in general some nth root of a number, of a complex number. You got this really kind of crazy looking formula here that tells you how to find the roots of any complex number, and we'll talk about what that's doing and what everything means here. So first of all, remember if you have a square root of 2, for instance, that's the same thing as 2 to the 1/2 power. Okay, or if you had a cube root of r, that's r to the 1/3. A fourth root of r would be r to the 1/4. So that's what this part of the formula is saying. So if you're doing like a fourth root, that would be 1/4. If you're doing a fifth root, that would be 1/5. Okay. Now the integer n would be whatever root you're looking at. So this is going to be the root. So if that was a fourth root or whatever, that's what the root is. Okay. Now this k is going to be an integer varying from 0, 1, 2, 3, 4, and so forth like that. And when you see that 2 pi, that's really representing the period of the sine and cosine. Okay, it's a crazy looking formula, but it's not that hard to crunch out. A couple of things that I would hope that you maybe remember from college algebra is this. So like for instance, if you had a polynomial function, basically if it had a degree of 4, then we said it had 4 zeros. You can think of those as roots, so it had 4 zeros. If you had a degree of 5, it had 5 zeros, and so forth, like that. So you're going to kind of have the same thing on this. If you have a square root, you have 2 roots. Now, you're not used to the square root of 1 having any root other than 1, but it has a complex root. The cube root of 1, you're used to that answer being 1. No, there's actually 3 answers. There's 3 roots. Fourth root of 1 has 4 roots, and so forth. So it's kind of weird. Okay, and it applies well with what you learned in college algebra. Okay, so for a square root, n is equal to 2. Okay, now what you always do on k is you always do 1 less than that. K is an integer, but since you're going to get 2 roots, you're going to use just 0 and 1. Okay, and you do get 2 roots on this. You might want to add that too. If you had a third root, n would be 3, k would be 0, 1, and 2. So you have 3 roots. When you get those 3 roots, you're going to vary that. Then if you have a fourth root, n is 4, k would be 0, 1, 2, or 3, and you're going to get 4 roots, and so forth. Okay, so let's see what we got on this now. We're going to look at the cube root of this complex number. And we're not going to say the cube root, we're going to say the cube roots. There's going to be 3 of them. Okay, so in this particular problem, first of all, here's r. So r is 125. N is going to be, we have 3 cube roots, so we're going to do that. Okay, so we're going to plug into this formula. Basically, I've got the formula all put together here. And then we're going to crunch this out. So let's go ahead and set this up. So first of all, replace r with 125. We're doing a cube root, so you're going to do to the 1/3 power. Then you're going to do the cosine of theta. Theta is 312 degrees. And we're going to do plus 2k pi over n. N is the third root, so that goes like that. Then we have plus I times the sine of 312 degrees plus 2k pi over 3, like that. So that's how you want to start, is by doing that. You want to know what everything represents. This is the radius. It's a cube root, so it's a 1/3 power, so the 3's go there. And got the angle, now we're going to vary k. All right, now you'll begin to see patterns in these problems as we do. Okay, so we're going to let k be 0 to start with, and we're going to work this out. So first thing we're going to do is we're doing the cube root of 125, which of course is going to be 5. Okay, right there. So when I bring this down, I'm going to get 5. Then I'm going to do the cosine of 312 degrees plus 2 times 0 times pi over 3 plus I times the sine of 312 degrees plus 2 times 0 times pi over 3. And then we're just going to write this in trig form to get our first root. So all we do is just clean it up and simplify it. So you'd have 5. Now see, that's going to go to 0. So what you're going to have really here, see, is you're going to have 312 divided by 3. So 312 divided by 3 is going to give 104. So this whole thing right here goes to cosine of 104 degrees plus I times the sine of 104 degrees, like that. Okay, so that's going to be the first cube root. Okay, who would have thought? Okay, now what does this mean? Now let me show you this too, because if you did this, like on your TI, if you did 5 times the cosine of 104 degrees plus I times the sine of 104 degrees, like that, and if you raise that to the 1/3 power, because you're doing if you raise this to the 3rd power, I'm showing you how to check. The way you check an answer to a cube root is you cube it. I don't know how well this is going to come out on the calculator, but we can find out. Basically, you would end up having, this is the a plus bi form of what we started with, is what you end up having, okay? So, a little bit hard to interpret on there with the calculator, but if you took this to the 3rd power, you would get this. But it's even better to show this. If you checked this, you would do de Moivres theorem. So let me show you how you would check this. If you checked, you would just say 5 to the 3rd cosine of 3 times 104 plus I times sine of 3 times 104, and you'd be back to where you began anyway. Okay, that's how you check an answer. Okay, if you don't know what I'm talking about, the cube root of 125 is 5, but the reason is because 5 to the 3rd is 125. That's what I did. I just took that answer to the 3rd power, and I'm back to the beginning, see? Okay? All right, now let's move on to the next one. Now what we do is next one's going to be 5. Cube root of 125 is 5, and we're going to do cosine of 312 degrees plus 2 times 1 times pi. And really that should be in, that really should be in degree form. The thing on this is we really need to write that as pi is 180 degrees, or 2 pi is going to be 360 degrees. So you can really just write this like this if you want to, since we're talking about the complex number. So we can say 2 times 1 times 180 degrees all over 3 like that. Okay, then we're going to say plus I sine 312 degrees plus 2 times 1 times 180 all over 3. Okay, so we can just do this on the calculator. You're going to see a pattern. I'm going to go ahead and crunch this one out very methodically to show you how this works out. So you're going to have 5 here. Now we're just going to do this on the calculator. We got 312 plus, see, this is really 360. Get that answer, and then divide that by 3, so you're going to get 224. So you have the cosine, 224 degrees, plus I, this is the same, so this is going to be plus I times the sine of 224 degrees. Okay, like that. So that is root number 2, believe it or not. Okay, right? So the next thing is, and if you multiply that out 3 times, you would get mathematically equivalent expression to this. Okay, then the next one, we're going to go to k is equal to 2. Okay, so we're going to say 5. Again, the cube root of 125 is 5. Then we're going to say the cosine of 312, go back to this original formula, 312. Now remember, 2 pi is really 360 degrees. So we can just say plus 360 degrees times 2. K is now 2. All over 3. Same thing here. Plus I times the sine of 312 degrees plus 360 degrees times 2 all over 3. Okay, use the calculator and let's see what we get. So we're going to do 312 plus 360 times 2. Get that answer, divide by 3. That's going to give 344. So we have the cosine of 344 degrees plus I times the sine of 344 degrees. Okay, like that. So that would be the 3rd cube root, like that. Okay, now I want to show you something on this. I want you to look carefully at these angles, 104, 224, 344. they have something in common. So if you do this, see, basically what's happening is you have 104 degrees, and then if you add, notice that if you do 224 on a calculator, if you do 224 minus 104, you get 120 degrees. Okay, so the thing that you'll kind of find the pattern on this that exists is it kind of goes like this. Okay, that first angle, I can call this theta 1, that's 104. Well, theta 2 is 104 plus 120, which turned out to be 224. Okay, then theta 3, the third angle, would be 224 plus 120 again, which is 344. So my question to you is, what in the world is that 120? Well, if you go back to the original problem, and if you look at the cube root, okay, remember we're doing a cube root. So if you do the period of a sign, 360, and divide by 3, it just means if you're dealing with a cube root, geometrically, the roots are off by 120 degrees. So you might write a note on that. So if you have a cube root, basically, every 120 degrees, you have a root. And that's going to be what's going to go in place for all these. So think about it. If you had a fourth root, you would have 4 groups of 90 to make 360. So on a fourth root, every 90 degrees is the angle. Okay, on a fifth root, if it was a fifth root, 360 divided by 5 would mean that every time 72 degrees goes by, you'd have another root, and so forth. If it was a sixth root, then the idea would be every time 60 degrees goes by, you would have an answer like that. Okay, so it's kind of interesting. Geometrically, these roots could be plotted out on the complex number system, and their angles would be 120 degrees apart. Okay, so that's how that goes. Kind of abstract, but it's very interesting, I think. Okay, now we're going to do some square roots of the next problem here. All right, and this one works out kind of like this. The very first thing that you got to do on a problem like this is you cannot use this formula unless you change this to the trig form. So we're going to go ahead and start by doing that. So we've got the complex number -1 plus square root of 3i, like that. And if I go through and just draw out a unit circle diagram on this, okay, that's going to go like this. Let's go ahead and do that. So we're going to basically just go left and up. I think we did this same thing a few minutes ago, if I remember right. So we go left and up a certain amount. So that complex number is represented like that. You can make your triangle. This would be the A part. So A is -1. This right here would be the B part. So that's square root of 3. So again, it's the triangle that's as easy as 1, 2 square root of 3. So that's 2 there. This time that's 60, like that. That's how that triangle goes. Okay, so what we're going to use is these two things. We're going to use the radius is 2, and then the angle in our r cis theta form, we're not going to use 60, we're going to use 120 degrees. Okay, like that. So when we move this to the r cis theta form, then we're going to have the radius 2 times the cosine of 120 degrees plus I times the sine of 120 degrees, like that. So that's going to be that form then, all right? So what we'll have then, to finish this up, basically is these fundamental ideas. We're going to start by just writing this in the complex form like this, and then we're ready to go through essentially and figure out what our roots are. So we're going to do square roots on this. Okay, so when we do that, we need to identify everything we need in the formula and go like this, and we'll look at a few shortcuts on this also. Okay, so it's a 2 is the radius. Okay, so we got a radius of 2. It's a square root, which is a second root, so that's also okay. It's a second root. Okay, so what we're going to do is crunch out the details on this. Now, one thing that might help you guys a little bit on this is since we're dealing with degrees here, you can think of this formula as 1 over n times the cosine of theta plus 360k over n. And then the same thing there. You just think of that as 360k. All right? Okay, so let's set this up then. So when we do this, we're going to always take... Okay, so what we'll do on this when we fill out the formula, we're going to do r, which is 2. And we're going to do that, to, of course, to the 1/2 power. So you want to start that way. To the 1/2 power, that's what this is. Okay, then we're going to do cosine of the angle. The angle we're working with is 120 degrees, so we're going to do 120 degrees plus, now instead of saying 2 pi, say 360 degrees, times 0, all over 2. And then same thing here, we're going to say plus I sine, exact same expression, 120 degrees plus 360 degrees times 0, all over 2, like that. Now you're going to learn to bypass this too, because what we said is in a circle, if you have a square root, that angle they go up by 180 degrees. So what you're going to have is the square root of 2. I'd just write this as the square root of 2. Then this is going to be the cosine. See, that goes to 0, so 120 over 2 is going to be 60 degrees. And then once you figure that out, don't waste your time crunching that out because it's going to be the same. So that's the sine of 60 degrees, like that. So that would be the square root of this complex number. So what we just found is, believe it or not, one of the square roots of -1 plus square root of 3i is this crazy thing. Now you could change that thing to the a plus bi form easy enough to get that answer, okay? Right now what we do is we just move on to the next one. Now I'm going to show you something different on this, because instead of going through this formula, really all you got to do is you just add 180 to that 60, and you're going to get 240 degrees. So the next square root, instead of going through this process, I just go square root of 2, cosine of 240 degrees, plus I times the sine of 240 degrees, like that. And then you're done. So it's a little faster if you just do it that way. Okay, so that's another square root. Okay, so we have that. Those are the two answers to that problem. Okay? All right, pretty abstract stuff, but that's what it is. Okay? All right, now this last problem is going to wow you. All right? Guaranteed. Hopefully this will make some connections on stuff you learn in college. Okay, so going back to your algebra background, if you're going to solve this problem, of course, what you learned how to do is isolate, and then, of course, take the cube root of both sides. And what you were used to doing in the past is saying, well, the cube root of 8 is 2 because 2 to the third is equal to 8. And you were done with the problem. Well, technically, there are 3 answers to this problem. If this was a x to the 4th, there would be 4 answers and so forth. And you learned that in a college algebra pre-calculus class. So what we need to do on this is we need to start by taking this number, the cube root of 8. So we're going to work with the cube root of 8, and that is going to have to be written like this, basically. Okay, so the first thing I want to do is let's consider what's going on with the number 8. Now, of course, really what happens is if you're in the a plus bi form, 8 is the same thing as 8 plus 0i. Okay? That just means that you're over 8. So you're there. That just means that the radius is 8, and the angle theta is going to be 0 degrees. So what we're going to do is we're going to crunch out this formula like this. Now I'm going to take a few shortcuts on this. Since we're dealing with cube roots, what you want to do is take that 360 and divide it by 3, and you get 120 degrees. That just means you're going to go like this. You're going to get an answer for theta. Theta 1 is going to be some value like t. And then the second value is just going to go up 120. The third value is just going to go up 120 again, and so forth. Okay, like that. So instead of crunching out that formula, it's actually much, much easier to learn how to do these problems like this. Instead of having k equals 0, k equals 1, k equals 2, just go like this. So what we're going to do is we're going to take the radius, which is 8, and we're going to take that to the 1/3 power, and then we're going to do the cosine. The first angle is 0, so we're going to do the cosine of 0 degrees plus I, come on, plus I times the sine of 0 degrees. Okay, like that. And we're going to work that out. Okay, so we're going to do that. That would be like the root number 1 is going to be that. I'm going to call that just root 1. Then the second root, root 2, is just going to be 8 to the 1/3 times the cosine of 120 degrees plus I times the sine of 120 degrees. Okay, then the last root, there's going to be 3 roots on this cube root. You're going to do 8 to the 1/3 times the cosine. Now you're going to go up 120 again to get 240 degrees plus I times the sine of 240 degrees. Now, in terms of the trigonometric form, we're already done. And really, we've done that. So we're going to take this to the a plus bi form, and we're going to do this. And we're going to do a couple of unit circle things, of course. So when we do this next step, we're going to have 8 to the 1/3 is 2. Cosine of 0 is 1. Sine of 0 is 0. So we end up getting 2 plus 0i, or just 2. So our first root is 2. We already knew that one. Okay, now what we got to do is crunch out the next two things. So I'm going to do a unit circle diagram over here to figure out the next two things. Okay, so if you're at 120, your angles go like this. Of course, this is 150, 135, 120. So the point on the unit circle at 120 is -1/2 square root of 3 over 2. So if I do the cosine of 120, I get -1/2. If I do the sine of 120, I do this. Okay, so I'm going to get, again, the cube root of 8 is 2, and then the cosine of 120 is -1/2, and then the sine of 120 is square root of 3 over 2. So I have I times the square root of 3 over 2. Like that, if I multiply it out, I get -2 over 2 plus 2i root 3 over 2. That reduces to -1 plus I root 3. So believe it or not, that's the next answer to the problem, okay? All right? So it goes like that. Okay, now we got one more answer to accomplish here, to put this together, so we got that. All right, so we got 2 answers now. All right, now on this one, what we're going to do, same thing, we're going to look at a unit circle. So 240 is actually this point on the unit circle, which is -1/2, and this time it's negative square root of 3 over 2. So again, when we do the cosine of 240, we get -1/2. When I do the sine of 240, I get negative square root of 3 over 2 like that. Okay? So when I do that now, I've got 2. Cosine of 240 is -1/2 again. I times negative square root of 3 over 2 like this. So that's going to be -2 over 2 minus 2 root 3 over 2i. So this answer is going to be -1 minus I root 3. It's the conjugate of that. Isn't that cool? Okay, those are your answers to your problem. And then I'm going to show you a couple other things to kind of help you make a few connections on that. So those are the cube roots. Now, so you didn't learn this in college algebra, but technically, if we do the cube root of 8, there's 3 answers. Okay, it's going to be equal to 2, -1 plus I root 3, or -1 minus I root 3. Who would have thought? Crazy, isn't it? Complex numbers. I mean, this whole idea it opened up just brand new areas of mathematics. Takes a while for a student to see that. But here's the idea. Now, here's how you would check. Of course, 2 to the 3rd is 8. So that's what we're doing. We're solving this equation. All right? So let me show you this. If I take the second answer, if I go -1 plus I times the square root of 3, and if I raise that to the 3rd power, I get 8 again. Crazy, isn't it? Then if I do -1 minus I times the square root of 3 again, and raise that to the third power, get 8 again. I just proved that those are the right answers to the problem. Okay, so that's it. I wanted to show you guys one other thing on this that's kind of interesting also. So I'm going to go back to this, and you can just watch this. So x to the third minus 8. There is another way you could do this problem. So you could also factor this. You may recall you have a difference of two cubes, and the formula for that is a minus b times a squared plus ab plus b squared, like that. So in this particular problem, what you would end up having is you would have, a is just x, b is just 2. So when you factor this would be something you probably did in intermediate algebra or something. You would have, for a minus b, you would have x and 2. So you'd have x minus 2 here. Then a is 2, so you square that. So that would be x squared. A is x, b is 2, so that's going to be plus 2x. B is 2, so 2 squared is 4, like that. So what you would find is, if you're doing this problem, then x cubed minus 8, you could kind of write your steps kind of like this. You could do x minus 2 times x squared plus 2x plus 4 equals 0, like this. And then what you'd end up having, of course, is x minus 2 equals 0, so that means x equals 2 as an answer. And then if you did x squared plus 2x plus 4 equals 0, you'd have to go the quadratic formula. So if you went the quadratic formula, you would have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Of course, an a is, of course, 1 in the problem. Okay? Now let me show you what happens. Now this will wow you. I mean, you're just going to be amazed by this one. This is negative 2 plus or minus 4 minus 16 all over 2. So that's going to be negative 2 plus or minus the square root of negative 12 over 2. That's negative 2i. Hold on, come on, I'm doing this too fast. Okay, so what you're going to have here is negative 2 plus or minus, and see if you're dealing with the square root of negative 12, that's I root 12, and then you can break that down into 4 times 3, so you get 2i root 3 like that. So it's 2i root 3 over 2. Now see if you reduce these 2's, just think about that. That would reduce to 1, that would reduce to 1, so you get x equals negative 1 plus or minus I root 3. Then I did that really fast, but the quadratic formula usually for trig students is not a big deal, so that's another way to solve the problem. Okay? All right, so I love this stuff. I love teaching this stuff. I love abstract math just tremendously. So, all right, that will be the end of this section. And the main thing that you want to be able to do is to Moivres Theorem for your final exam. That's the #1 thing. All right, have a good day.